Hello and welcome back. In this video we're going to see more examples where we're going to find the kernel of a linear transformations. So first start with this one of the easier example to find kernel. So here we have T is a linear map from R2 to R2 and is defined as T of xy is 0 0. So all vector of R2 goes to the 0 vector of R2 and we have to find the kernel of T. So what was the kernel of T? So kernel of T, so let me write it down. So kernel of T is basically collection of all vectors of R2. So they are all vector of R2 which basically transfer, so which basically map, so this vector map to the vector 0 0. So in this example if I put, so here what it says, if I put any xy, so for example if I take xy as equals to 2 3, so what about 2 3? So T of 2 3 goes to, so you can see that here we have x and y, so x is 2 and y is 3 and it always goes to the vector 0 0. So for any vectors, so x y are any real number, so for any x y it always goes to 0 0. So kernel of T basically the collection of all x y, so all x y, because all x y goes to the vector 0 0, so kernel of T basically whole of R2. So kernel of T, so let me write it down, kernel of T is a whole of R2 because all vector of R2 is goes to the 0 vector of R2. So in this example kernel of T is the 0 0. Okay, let's do some difficult problem. Okay, so here we go. So first let me erase this part, so erase it. So here we go. So suppose we have an example, so T is a linear transformation. So let me write down that this is an example. So example, so T is a linear transformation which map the vector of R3 to the vector of R3. And how it is defined? So it is defined by for any x2 y2 x3. So any vector of R3 goes to the vector. So what is goes to the vector. So first coordinate of the vector is the addition x1 x2 x3. Second one is 2x1 plus x2 plus 2x3, and third one is x1 plus 2x2 plus x3. So if I put any point, so for example if I put T of 1 2 minus 3, so what it is goes, so here x1 is 1, x2 is 2, x3 is minus 3, so it goes to 1 plus 2 minus 3. Next x1 we have 2 into x1 is 1 plus x2 is 2 and plus 2 into minus 3, comma, what is x1? 1, x2 is 2, x3 is minus 3. So it goes to the point 0 and we have 2 plus 2 is 4 minus 6, so it goes to minus 2, and here we have again 0, so it goes to the point again 0. So I think I have made a mistake. So here we have 2 into x2, so 4, 5 and 2, so it goes to the point 0 minus 2 and 2. Sorry for my mistake. So that's how the mapping is defined. What we have to find? We have to find kernel. So kernel is, let me remind you, kernel of T is the all x y. So here we have x1 and y is basically, so x2. So let me erase this one. So what we have to do, so we have to do right here, instead of x1 xyz we are going to write x1 x2 and x3 because we have three components. So this is a vector of R3. So this map to, so it's mapped to x1, x2, x3 goes to the 0 vector of R3. So which one is the 0 vector of R3? So 0 vector of R3 is 3 0. So 0 0 0. So all components of the vector are 0. So we are talking about all such vectors which goes to the 0 vector of R3. Okay, so how it is defined? Suppose we have an element. So for taking an element, so let us take A, B and C belongs to kernel of T. Because it belongs to kernel of T, then it satisfy the property of the sets. So that means it goes to T A of B C is equals to the 0 vector. So what is the T A B C is defined? The function is defined in this way. So definition is given. So it says that first component of the transform vector have to be equals to here x1 is A, x2 is B, x3 is C. So it will be A, B plus B plus C. So next second component will be A into x1. So x1 is A plus x2, x2 is B plus 2, x3 is C, comma, and third component is x1. So x1 is A plus 2x2. So 2x2 is a B and x3 is C. So C. So these have to be equals with 0 0 0 because we have two vectors which are equal in R3. So each component of the vector have to be equal. So for left hand side of this equation, so left hand side means in this side, and right hand side means the right hand side of my body. So here in this way, so A plus B plus C have to be equals to 0. 2A plus B plus 2C, these also have to be equals to 0, and A plus 2B plus C, that's also have to be 0. So we have three equations, 1 2 and we have 3. So we're going to solve first two equations, and after that if we get the value of ABC, we put it on the third equations. So if I do in this way, so what we get basically, we get AE by, so if I write it down, so let me erase the upper portions, or just take me erase me out. So here we go. So we erase this part. So I think you remember where it was. So just erase this part from what we get from 1 and 2. So let me write it down. So from 1 and 2, from 1 equation 1 and 2, we get A equal by, let me write A by B equals to C. So if I do this way, so it will have 2 into C minus 2 minus 1. So it gives me, what it gives basically, it gives me 1 basically. Second B, so what we are doing, so we are just using some methods from your system of linear equations course. So from there we get B equals to 2 2, and it gives me 0. And just do it for yourselves, pause the video and do it for yourselves, and you will find that after that this will be minus 1. So suppose this is to equals to K, say, so K is any real number, so K is a real number. So what we get, so we get A equals to K, B equals to 0 and C equals to minus K. Okay, put the value in the equation 3. So from 3, so let me write it down. So from 3, from the equation 3, so we get, so sorry, I have written over here Roman 2, and here we have written just this numerical 2. So we get the same thing. So here we get from 3 we get what we get. So we get, if I put the value K plus 2 into 0 minus k equals to 0. So it satisfies the equations basically. So it satisfies the equation. So this is the solution of our kernel. So let me write down the kernel. So it's satisfy the equations 3. So here we go. So just give me some times to erase the whole part. So what we have, so kernel of t, now kernel of t is collection of all a b c, because we have taken a b c's and any elements of kernel. So here a have to be equals to k, b have to be equals to 0, and c have to be equals to minus k, and k is any real number. So if I put the value of a, b and c, what we get, a equals to k, 0 minus k, and k is any real number. So if I write it more formally, so we get k into 1, 0 minus 1. So k belongs to R. So basically kernel of t span set or span by the vector 1, 0 minus 1. What is span? Span means the linear or type of linear combinations of this vector. So linear combination means this vector, before that we have a scalar. So here you can see that the vector and scalar. So this is the one of the linear combinations. So it varies with different value of k. So this is the span of this vector. So kernel of t is spanned by these vectors. So we know that span of vectors is a subspace. So you can see that kernel of t is a subspace. So basically we have a theorem. So from there, if you see in previous example where we have find out a kernel of t, and from each example also from there we have a theorem, we can prove that. But just let me state that. So it says that. So let me state the results. But before that, let me erase all that parts. So erase it. So give me some times. I'm sorry that I'm taking your times, your basically your net balance. So I'm sorry for that, but I have to go through all this process. So here we have the good results. So we going to state two results from kernel of t. They are very important. So beautiful results. First one is very beautiful. So result 1 says that if we have a linear mapping, so t from v to w be a linear mapping, so it's a linear mapping, then we already see that kernel of c, we already seen that kernel of t is a subset of b. So here we have some extra step. So it says that kernel of c not only subset of b, it's also a subspace. So that's the very important thing. So kernel of t is a subspace. So it's a vector space, subspace of t. If you go through the previous examples, what we have find out in kernel of t, each of that example we have seen that kernel of t is a subspace of t. So just let me remind you, just go through the previous video, and you will find out that kernel of t is a subspace. So we have already discussed in this video that kernel of t, for the last part, kernel of t is generated or generated or spanned by the vector. So that's a subspace. So it says that for any linear transformation from a vector space v to w, kernel of t is always a subspace of t. So here is a very beautiful results. So we have another very good results. So it says that, so result 2 so result 2 says that if if t from, so suppose let me write down t from b be linear mapping. So I am just not writing let to linear mapping, just you will find more formal way of writing in our notes. So t from b is a linear mapping, then t is a one-to-one mapping, means t is injective. So t is an one-to-one map. So here we have an one-to-one mapping if and only if and only if kernel of T only contain the zero vector of V. So where theta is the zero vector, theta where is this? Oh yeah, yeah it is. Theta is the zero vector of V. So it says that if T is a one-to-one, if T is one-to-one, which means if I take any 2 points, so it says that if I take any point alpha and beta from V, so if T of alpha is equals to T of beta, so this implies alpha equals to beta, and this is true for all alpha beta belongs to V when it is one-to-one. So this implies when one-to-one, it will implies that kernel of T contain only one vector, a zero vector of V. And in another way, so in converse way, if kernel of T is contain only the zero vector, then T is one-to-one. So this implies T is one-to-one. So to check a mapping is one-to-one not, we have to find out the kernel of this linear mapping. So a linear mapping is one-to-one or not. For that we have to check the kernel of T is only the singleton set contain the zero vector of V or not. So we will go to the next example where we're going to find that it is one-to-one and kernel of T contain the zero vector. So for that, so let's go to that example.